Thank you, Claudia. Good morning, everyone. So I would like to mention that I will mostly be talking about the Miro measurements themselves, actually, and so this is really a presentation on behalf of the whole team. So Miro is like a mini radio telescope. It has a 30 centimeter dish, and it has a receiver with two different bands at 190 gigahertz and 560 gigahertz. So we measure the continuum in both bands, which means that we are seeing the thermal emission from whatever we are looking at. And also the sub-millimeter channel is connected to a truck transport spectrometer, which allows us to do high-resolution spectroscopy of the rotational lines of water with isotopologues of oxygen, CO, ammonia, and methanol, for which we see three lines. So we have a very tiny beam, which has implications for the observation strategy that I'll get to in a second. And the science objective of Miro is really to study the structure and evolution of the coma and subsurface temperature as a coupled system to understand heat transport and outgassing from the nucleus. So in 2014, we've been pretty busy. We have done the recommissioning of Miro at the end of April, and that was why we are still really, really far from the comet. And then we had the approach phase basically until the beginning of August, when we closed in really, really fast, or rather, the comet was catching up to Rosetta very quickly. And so that was a time where we had very nice views of the comet as an ensemble, and primarily looking at the coma in order to measure global gas production rate and its evolution with time. Then after the rendezvous phase in August, we have been since then in very close quarters with the comet. So that's great because that gives us really high spatial resolution. But when you look at the images, I'm not sure if you can see the Miro beams here, but they're really, like basically from 100 kilometers, they're there. And at 10 kilometers right here, well, it's basically a dot. So we have a reverse of a needle in a haystack problem, where we are the needle and we have to scan the whole of the haystack in a finite amount of time because the nucleus rotates really fast and everything changes quickly. So that was observationally challenging, but that gives us really high resolution data. So I will go in more or less chronological order, starting with our very first water detection. That was on June 6 and 7 for 22 hours integration from 360,000 kilometers distance, a phase angle of 35 degrees. So basically we had the sun in our back. And you can see here the spectrum. So you have the power received as function of the Doppler velocity and a very clear line. So the signal to noise ratio is of course not great, but that's clearly a detection right there. And you can see that the line is actually blue shifted. This blue shift means that based on the situation we were at, the observation geometry, almost all of the gas that we were seeing was actually coming towards the spacecraft and not away from us. So that was the first indication that we have more or less hemispheric outgassing, and almost only from the day side from this comet, with a velocity around 700 meters per second. And all of our observations since actually support these results. So with this first detection, we had an outgassing rate on the order of 10 to the 25 molecules per second. That's about the equivalent of 2 cups of water that you vaporize and dump into space every second. Then as we got close in, of course, our signal-to-noise ratio increased a lot. As you can see here, an observation from 130,000 kilometers. And as we got really close, for example, you see here in August 19th, from 80 kilometers, we actually were seeing the nucleus in the background. So instead of having the lines in emission, we're seeing the lines in absorption in front of the nucleus. So that was an interesting change in the spectral behavior. Also, at that time, the water column density was becoming so high that it was optically thick. And so we chose to actually use the water 18O line that we could detect in order to have better sensitivity to our outgassing rate. And so we can see between June and August an increase by a factor of 4 in the outgassing rate. While we were at intermediate distances, here you have 13,000 kilometers, we could start to see a diurnal periodicity. And that's because our integration times were then short enough that we could take advantage of this to map out everything as a function of the phase, the rotation phase of the comet. And so you can see that we have these patterns, which does not exactly repeat itself, but clearly shows 2 maxima and 2 minima per comet rotation. And so the interpretation that we make of this was that it was due to primarily to the nucleus shape, variability in the installation, and probably the distribution in ice. And the preliminary model was generated by Bjorn Davidson that was using ice solely located on the neck and other spots of the surface. And you can see that, of course, that was preliminary, so it's not exactly matching the data, but the general trends are there. So that was quite encouraging. And this suggests that we have some spatial variability of the outgassing. We had that from afar. Once we were close, that became really, really clear. And what we see here in this observation from about 80 to 90 kilometers is that in this plot you have the water column density in blue, the submillimeter continuum temperature in red, and the insolation in as the dotted black lines. And you can see that the temperature and the insolation follow each other fairly closely, which is what you would expect. But there is no obvious correlation between the temperature and the insolation or the water column density. We also see up to a factor of 20 of amplitude in variation in the water column density, depending on where we were looking. And if you look at those peaks, 1, 3, and 5, you can look here. The red dot is actually the footprint of the Miro SMM beam on the nucleus, and you can see that all of these were on the neck or very close to it, whereas the other 3 were a little further away from the neck. So this suggests that we have strong variation in outgassing depending on the location on the nucleus, and also the neck region has column density that are several times higher and also slightly higher gas velocities than elsewhere on the comet. So once we got really close as well, you have here a map that was initially primarily done for thermal mapping that was doing scans back and forth across the nucleus that way and across the coma. And you have here the location of the nucleus at the center of this time and a map of the water column density. And you can see that very clearly it's much higher towards the sun and above the neck than elsewhere, and there is little to no outgassing on the dark side of the comet, so to speak. So as I was mentioning, that was an observation primarily done for the continuum measurements. And the last thing I want to emphasize on the gas part before moving to that is that we have seen an increase in the production rate between the approach phase and now, and also this very spatial heterogeneity of the outgassing. Now moving on to the thermal mapping, so that's a different observational strategy, as I was saying, scanning really fast back and forth along the nucleus. So you have here an example of an excerpt of a thermal map done in the sub-millimeter channel that was on August 13th from about 100 kilometers distance. And the first thing to note is the scale. You can see that our sub-millimeter temperatures in this scan did not go above 130 Kelvin. And that's because, unlike Vertis, we are not sensing directly the surface temperature, we're actually sensing the subsurface temperature. And the depth at which we are actually probing depends on the dielectric properties of the materials and the wavelength. Also, this map actually shows the projected antenna temperatures and the projection of the Shape 2 model with the insolation on it. And you can see that there is a very neat correlation between the patterns that we see in the antenna temperatures and the topography and the insolation at first glance. Lastly, we see on the southern regions, which have not seen any light yet, and therefore have not been imaged by OSIRIS, that there is some parts of the nucleus, and that's areas that are in polar night. And they were not included in Shape 2, but as Holger has shown earlier, they are now working into including them in the more recent versions. So using this thermal mapping data, we can actually constrain the thermal properties. And what I'm showing here is the brightness temperature as a function of local solar time for the sub-millimeter channel and the millimeter channel at 20 to 30 degrees latitude north, which are the black dots, and 20 to 30 latitude south, which are the red dots. And they both, in both channels and both latitude bins, we are seeing clear sinusoidal diurnal variation, which is expected, and the amplitude is actually much larger at the sub-millimeter wavelength than the millimeter. That's because the millimeter is sensing much deeper than the sub-millimeter. It's mostly wavelength effect. Also, by looking at the average of these two latitudinal bins, you can see that there is a seasonal effect as well. And I won't go into the details of the modeling, but I will encourage you to check the poster tomorrow that we have in the Rosetta poster session. But we can derive from these measurements thermal inertia in the order to from 5 to 40 MKS. And we also, based on this thermal inertia, we can infer a diurnal skin depth on the order of a centimeter, which is close to our sub-millimeter emission depth. So by putting all of this together, what can we say really about ice? First of all, the gas production rates that we have seen are such that the solar flux that the comet has been subject to so far is high enough that we only need very little coverage, under 1% of ice coverage distributed on the surface will be sufficient. Also, the fact that we are seeing this diurnal activity dominantly in the outgassing implies that there is water ice reservoirs within the diurnal layer. And based on the thermal inertia that we can measure, we can infer that this diurnal layer is going to comprise the very first few centimeters of the surface. And lastly, there are very large negative thermal gradients within the diurnal layer for that kind of thermal inertia. It's up to 50 Kelvin in a centimeter, so that's really huge. And that means that the deeper the ice is located, the more ice would need to sublimate in order to actually generate the production rate that we see effectively. And I guess I'm out of time, so I will leave the conclusion slide and thank everyone for your attention. Thanks, Rosetta, Isaac, and LESIA. Thank you.
Okay, the paper is now open for questions. Questions? You have to go to the microphone.
Well, in fact, we have to consider that the comet is evolving as you can retrieve from measurements of the water vapor prediction at the last perihelion. You can find that you can estimate that maybe a layer of about 2 meters is lost at each passage. And so this kind of measurements show also that, in fact, the ice is perhaps in the very few nearby centimeters, but this is going to be peeled off. So we have to think everything that we see now, the pictures of Osiris, we have to think that it is going to evolve enormously. And so it is not like in geology where everything is stable for millions of years. This is going to evolve. And so we have always to think that, in fact, it is peeling off a lot at each passage.
Yes, you're very right, Jean-Loup. Thank you for making this comment. It's true that with production rates that are going to increase by 2 orders of magnitude compared to what we are seeing now, there's going to be a lot happening. But also the sun is going to be on the completely other side of the comet. So I think we might see something that looks entirely different. We'll see.
Are you able to spill us any secrets about methanol or some other substances?
So what I can say is that based on the Rosetta measurements, we are in a situation where for CO and ammonia, we're really, really borderline to what we would expect to be able to detect. And we're still searching the data for that. We have no clear evidence. And we may have seen some methanol, but that's still very tentative, and we're still working on the data. We are waiting for the production gas, actually, for the production rates to actually increase. That will really help. Because we are extremely sensitive to the water line, but those other lines are actually much weaker.